An overhead crane moves a 30-ton steel beam across a Pittsburgh mill floor. The beam is suspended 40 feet in the air. It is 1927. Below the beam, 3 workers are positioning supports for the next lift. They have done this 1,000 times. The crane operator sits in a cab 50 feet away. He cannot see the men directly below the load. He is looking through dirty windows, watching hand signals from a ground guide. The cable holding the beam is 1-inch thick steel wire rope, rated for 50 tons. It has been in service for 8 years. The last inspection was 6 months ago. The inspector walked the cable, looking for visible damage, kinks, broken outer wires, obvious wear. He found nothing. The cable was approved for continued use, but inside the cable, where eyes cannot see, 30% of the load-bearing wires have broken from fatigue. The remaining wires are holding 30 tons. The math still works until it does not. The crane continues its travel. The beam swings slightly. The stress on the cable increases. 1 more internal wire breaks, then 2 more. Then the cable separates completely. 30 tons of steel falls 40 feet. Gravity accelerates the beam to 35 miles per hour in 1.6 seconds. The workers below hear nothing until impact. No warning, no time to move. The beam hits the first man directly on the head. Instant death. The beam bounces and strikes the second man in the chest. Crushed sternum, dead in seconds. The third man is hit by the bouncing end of the beam. Broken spine, dead before the foreman arrives. The crane operator does not know what happened. He felt the load release. He thought the beam was set. He continued the cycle. By the time he climbed down from the cab, all 3 men were dead. This is the story of the overhead crane. The machine that lifted the weight of American industry 40 feet into the air and held it there with steel wire rope. The equipment that moved million-ton loads across factory floors while workers walked beneath. The system that relied on cables you could not fully inspect and operators who could not see what they were killing. Before we are done, you will see how overhead cranes built the steel mills and shipyards of America. You will see what happened when cables failed without warning, and you will see why the men walking under suspended loads had no choice but to trust physics they could not verify. If you enjoy these stories, then support this channel by subscribing and liking. Thank you. Now, back to factory iron. Bethlehem Steel, Pennsylvania, 1890. Charles Schwab is building the largest steel mill in America. The mill needs to move massive quantities of steel. Ingots weighing 20 tons, beams weighing 30 tons, plates weighing 40 tons. Moving this material by hand or cart is impossible. Moving it by locomotive is too slow and inflexible. The solution is overhead cranes, bridge cranes, gantry cranes. Massive structures span the width of the mill building. A bridge travels the length of the building on rails. A trolley travels across the bridge. A hoist hangs from the trolley. A cable runs from the hoist through pulleys to a drum. The drum winds. The cable lifts. The load rises. The system is elegant. 1 crane can service an entire bay. Multiple cranes can work simultaneously without interfering with ground operations. Workers and materials can move freely beneath the crane. The crane operator sits in a cab mounted on the bridge. He controls movement with levers, bridge travel, trolley travel, hoist up, hoist down. He can position a load anywhere in 3-dimensional space within the crane's coverage area. The precision is remarkable. A skilled operator can set a 30-ton beam within inches of its target. But precision requires visibility. Visibility from a crane cab 40 feet up, looking through small dirty windows while trying to see directly below the load, is limited. The cables are the weak point. Everything depends on the cables. A cable is not a solid piece of steel. It is a rope, woven from dozens of individual steel wires. The wires are wrapped into strands. The strands are wrapped around a core. A typical 1-inch crane cable contains 114 individual wires. Each wire is thin, about the thickness of a pencil lead. The strength comes from the combination. 114 wires working together can hold 50 tons. But if wires break, the load shifts to the remaining wires. As long as enough wires remain intact, the cable holds. When too many wires break, the cable pulls, suddenly, catastrophically, without warning. The problem is inspection. You can see the outside of the cable. You can see broken outer wires. You can see kinks and deformations, but you cannot see inside. You cannot see the internal wires that are breaking from fatigue. Steel wire fails from repeated stress cycles. Lift a load, lower a load, the wire flexes. Microscopic cracks form. Over thousands of cycles, the cracks grow and the wire breaks. One wire breaking does not matter. 10 wires breaking does not matter. But when 40 wires break, when 50 wires break, the remaining wires cannot handle the load. The cable parts. The load falls. Cable manufacturers recommended replacement based on time in service and load cycles. Replace cables every 2 years. Replace cables after 100,000 load cycles. These were recommendations, not requirements. Mill owners made their own decisions. A cable that looked good on the outside stayed in service. Replacing cables cost money. The crane had to be taken out of service. Production stopped. A new cable cost hundreds of dollars. Labor to install it cost more. And the old cable looked fine. No visible damage. Why replace something that is not broken? So cables stayed in service. 3 years, 5 years, 8 years. The outer wires would break occasionally. Maintenance would cut off the damaged section and re-terminate the cable. Shorter now, but still functional. Still holding loads, still looking acceptable from the outside. The accidents followed a pattern. A crane would be a normal operation, moving loads it had moved 1,000 times before. The cable had been inspected recently and found acceptable. The crane lifted a load, not an unusual load, not overweight, just a normal lift. Then the cable parted, and the load fell. Workers below died. Investigators would find the cable had extensive internal wire breakage, 40%, 50%, sometimes 60%. The remaining wires had been holding loads far beyond their rated capacity. They held until they did not. In 1905, a crane at Carnegie Steel in Pittsburgh dropped a 25-ton ingot. The cable parted during a routine lift. The ingot fell 35 feet and landed on 2 workers. Both died instantly. The investigation found that 58% of the wires in the cable were broken. The cable had been in service for 7 years. The last inspection, 3 months earlier, had found no issues. The inspector saw some broken outer wires but judged them within acceptable limits. He could not see inside the cable where the majority of breaks had occurred. In 1911, a crane at a Philadelphia shipyard dropped a 40-ton boiler section. The cable parted without warning. The boiler fell and crushed 4 workers. The cable had been in service for 9 years. It had been inspected 6 months earlier. The inspector noted some wear but approved continued use. After the accident, analysis found 62% internal wire breakage. The cable should have been replaced years earlier. In 1918, a crane at Bethlehem Steel dropped a 30-ton steel plate. 3 workers were killed. The cable had been in service for 6 years. A recent inspection had found it acceptable. Testing after the accident showed 53% wire breakage. The pattern was consistent. Cables that looked adequate from outside inspection were failing internally. Workers died under loads that appeared to be safely suspended. But cables were not the only killer. Hooks failed, shackles failed, slings failed. Any component in the load path could fail, and workers could not inspect any of it while it was 40 feet above their heads. They had to trust the system, trust the inspection, trust the maintenance, trust the crane operator they could not see, trust the equipment that held tons of steel over their heads while they worked. The visibility problem made everything worse. A crane operator in his cab could not see directly below the load. The load itself blocked his view. He relied on a ground guide who used hand signals to direct the crane. Move forward, move back, move left, move right, lower, stop. The system worked when everyone understood the signals and paid attention. It failed when communication broke down, when the ground guide was distracted, when the operator misread a signal. when workers entered the danger zone without the operator knowing. In 1913, a crane operator at a Gary, Indiana mill was moving a beam. The ground guide signaled to lower. The operator began lowering. A worker walked under the descending beam to retrieve a tool. The ground guide did not see him. The operator could not see him. The beam descended. The worker looked up at the last second. The beam struck him in the head. Skull fracture. Dead within minutes. The operator did not know he had killed someone until the ground guide ran to his cab shouting. The noise in mills made communication harder. Shouting did not work over the sound of furnaces, rolling mills, and multiple cranes operating. Hand signals were all operators had, and those signals required a clear line of sight. If steam or smoke obscured the view, if the sun was in the operator's eyes, or if the windows were dirty, signals were missed. Loads moved when they should not. Loads stayed stationary when they should have moved. Workers were caught between moving loads and stationary structures, crushed against walls, caught between the load and the floor, struck by swinging loads. Swinging loads killed regularly. A suspended load is a pendulum. It wants to swing. A skilled operator anticipated the swing and corrected for it. An inexperienced operator would overcorrect. The load would swing harder. The swing would build. A 30-ton load swinging at the end of a 40-foot cable has tremendous momentum. If it hits something, it does not stop. It crushes. Workers were struck by swinging loads and killed instantly. Walls were damaged, equipment was destroyed, and the operator in his cab could not always see it happening. Some mills tried to improve safety. They painted red lines on the floor, marking danger zones around crane coverage areas. Workers were supposed to stay out of the red zones when cranes were operating. This failed because the work had to happen inside those zones. You could not unload steel, position supports, or do any of the actual mill work from outside the danger zone. The red lines were crossed constantly, and they became meaningless. Other mills tried installing warning bells on cranes. The bell rang when the crane was lifting or moving a load to alert workers to danger. The bells rang so frequently that workers stopped hearing them. The sound became background noise. When the bell actually mattered, when a load was directly overhead, nobody reacted. In many installations, the bells were disabled because they were annoying and useless. A few progressive mills implemented restricted zones. When a crane was operating in a specific area, all non-essential workers had to leave that area. Only the workers directly involved in the lift could remain. This reduced casualties, but it also reduced productivity because workers had to constantly evacuate and re-enter areas. Mills tried this for a few months and then abandoned it. Production mattered more than keeping workers clear of danger zones. The economics of crane safety were brutal. Replacing cables before they failed cost money, and it cost production time. Installing better inspection equipment cost money. Training operators cost money. Hiring ground guides dedicated to signaling cost money. The alternative was occasional accidents. The math was simple. In 1920, a worker's life was worth about $800 in wrongful death settlement. A new crane cable cost $300, but it required 8 hours of crane downtime. Crane downtime cost approximately $2,000 in lost production. The mill could kill 2 workers and still save money compared to replacing the cable proactively. The regulatory response was slow. Most states did not require crane inspections until the 1930s. Even then, inspections were visual only. Inspectors were told to look at the cable, look for broken wires, look for deformations. Pass or fail based on what you can see. Internal wire breakage could not be detected. The inspections gave a false sense of security. Cables that passed inspection still failed. Workers still died. The technology to detect internal wire breakage existed. Magnetic testing and X-ray testing could identify broken wires inside the cable. But the equipment was expensive, and testing was time-consuming. Mills did not adopt it voluntarily. Only after major accidents, after public pressure, after lawsuits, did some mills begin implementing more advanced cable inspection. And even then, adoption was sporadic. Large modern mills might use magnetic testing, Smaller mills, older mills, and mills trying to minimize costs stuck with visual inspection and hoped the cables held. Experienced workers knew the danger. They had seen loads fall. They had seen cables fail. They had seen men die. They developed informal safety practices. Never stand directly under a load. Always watch the load when it is moving. Stay clear of the landing zone. Work quickly and get out. These practices reduced casualties, but they could not eliminate them. Sometimes you had to be under the load. Sometimes the job required you to position something while the crane held it overhead. You did the work and hoped the cable held. Usually it did. Sometimes it did not. The overhead crane era did not end. Cranes are still essential in steel mills, shipyards, and manufacturing facilities worldwide. The technology improved. Modern cranes use better inspection methods. Magnetic testing is standard. Cable replacement schedules are enforced. Operators have cameras and sensors that show them what is below the load. Proximity alarms warn workers when they are in danger zones. Load limiters prevent overlifting. The modern crane is dramatically safer than the 1920s version. But we still have accidents. Cables still fail. Loads still drop. In 2023, a crane at a shipyard in Virginia dropped a 20-ton container. Cable failure, 2 workers killed. In 2024, a crane at a steel mill in Alabama dropped a beam. Hook failure, 1 worker killed. The technology is better. The inspections are better. The regulations are stricter. But physics is physics. Steel wire fatigues. Components fell. Loads fall. The total death toll from overhead crane accidents is impossible to calculate precisely. Records from the early 1900s are incomplete. Many deaths were attributed to industrial accidents without specifying the equipment involved. But estimates from insurance industry data and safety reports suggest that overhead cranes killed at least 1,200 workers in American industry between 1890 and 1940. That is 50 years. That is 2 deaths every month. A cable snaps, a load falls, a worker is crushed, a family is notified, every 2 weeks for half a century. Most were men between 20 and 45. Most had families. Most were experienced workers who understood the risks, but had no choice but to work under the loads. They needed the job. They needed the pay. The mill needed them under the crane. The work required proximity to danger. They walked under 30-ton loads, suspended by cables they could not inspect. They trusted systems they could not verify. They relied on operators they could not see. And sometimes the cable parted. The load fell, 40 feet, 1.6 seconds, 35 miles per hour impact. No warning, no time to run, just physics. The cranes are still running. Walk into any steel mill today and you will see them. Giant bridges spanning 100-foot bays, moving loads of 50, 80, 100 tons. The hum of electric motors, the rattle of chain, the warning horns. But the operators now have cameras. The cables are tested magnetically every month. The inspection standards are strict. The workers wear hard hats and stay in marked safe zones when possible. The culture changed. OSHA exists. Safety matters. Workers are not expendable. But the fundamental truth remains. Overhead cranes hold tons of steel in the air with cables. Cables wear, cables fail, and when they fail, loads fall. We have made it safer, we have made it rarer, but we have not made it impossible. Progress has a price. We look at modern industry and see efficiency. Cranes moving massive loads with precision, just-in-time delivery, optimized workflows, clean facilities. But underneath it all, if you look close enough, you will see the ghosts. You will see the 3 men in Pittsburgh under the falling beam. You will see the workers who trusted cables that looked fine from the outside. You will see the crane operators who could not see what they were killing. They do not make them like that anymore. Not the men. The cranes are better. The inspections are better. The cables are better. But the steel is the same. The gravity is the same. And when tons drop from above without warning, the outcome is the same, instant, final. Physics does not negotiate.